So describe the transformation of f represented by g, then graph each function. So if this is my given function, that's a what?
Cortex.
Cortex. Okay, cortex. So, oh, this is example 2 on the 4-7 notes. So I'm going to graph the parent, and I can't fit that like 2, 16 point on the graph. I know it's like way up here. What's important is that when I do graph this, I show that the graph as I go from this point out to the next doesn't hit the 2. Okay. You can also change your units, like you don't have to be counting by ones, if that makes sense. You just don't have to. And these are really the 3 points I'm looking for, and I know that these 2 additional points are out here, I just haven't hit them yet. Okay. Do you guys see what I'm saying about you don't want the graph to sort of like cross this value yet? It shouldn't happen until the 16th. So that's f of x. Who can tell me that there's 2 transformations to make g of x? Who can tell me them? Serena?
One of them is a reflection across the x-axis.
Okay, so this negative is a reflection across the x-axis. Yes. Okay. Jim?
A vertical shrink by a factor of 4.
Vertical shrink by a factor of a 4.
Up 4.
Right.
Okay.
I think it should be 4 because if you shrink, that implies it's smaller than 1. So I think it's redundant to say a shrink by a 4th, but it is what it is. I want to follow suit with your book.
Okay.
So I want to take these points and I want to reflect them. So the whole graph's going to be upside down, right? And then shrink it by a 4. So I'm going to take the vertical height of the points and compress them by a 4. Okay. So the 0, 0 is going to stay. Okay. The out 1, down 1 is going to now be out 1, down a 4. So it's going to be really kind of squat, right? Really close to the x-axis. And then instead of out 2 up 16, it's going to be out 2 down 16, but that down 16 I'm compressing by a 4. So it's going to be out 2 down
4.
4. Good. But that sort of like flattening to the x-axis behavior is still going to kind of exist between those values, the 0, the 1, and the negative, right? And that is g of x. So I'm just going to kind of quickly hop to this one, okay? So here's something I'm going to recommend. Every single even power polynomial in the set of notes, we're going to treat like a 4th power. So if you have a 6th power or an 8th power, treat it like a 4th. The reason being that it's going to look similar enough, but higher than 4th power, gosh, it's just really hard to graph, okay? I'm going to say the same with an odd degree power. Let's treat them all like cubics, even if in your notes you have a 5th degree. So this 5th degree, I'm going to treat this like a 3rd degree. I'm going to treat this like a cubic. So I'm going to treat that like a cubic, that like a cubic. So I would suggest you do that in your notes as well. Okay. So I'm just going to start with graphing the parent function, the cubic parent, which you guys should be pretty comfortable graphing by now. So my critical point 0, 0, 1, 1, 2, 8, negative 1, negative 1, negative 2, negative 8. Okay. So there's the parent, that's my f of x. Now you have a couple options here, okay? The way this is written, do we all see the down 3? Right, we all see the down 3? Down 3 is not so bad. Now the way this is written, it looks like a horizontal transformation, right? This appears to be, does anyone know what kind of horizontal transformation that is? It's a horizontal shrink by
2.
Remember, we're thinking about what x would have to be. X would be have to be half as big, so that when you multiply it by 2, it gives me the same output. So it's a shrink by a half. My suggestion is, if possible, get rid of those parentheses by expanding out the term. In other words, 2x cubed without the parentheses is what? So if I expanded that out, 2x times 2x times 2x, what do I get? 8x cubed with no parentheses. The benefit to doing that is then you see that when I do this, this is also a vertical stretch by 8. What that means is if you prefer to graph a vertical stretch by 8 rather than a horizontal shrink by a half, you can do that. In other words, a cubic, because the numbers are cubed, they grow a lot faster this way than they do this way. So if I were to take it horizontally and press it in by a factor of a half, that's going to appear the same as if I stretched it this way by a factor of 8. Okay? Because there's not like a 1-to-1 ratio on the x and the y. So if I were to do that, if possible, this can get a little hairy, but if possible, I would recommend you doing this because it's more intuitive. Okay? So we're going to take these points, we're going to move them. What are we going to do first, the stretch or the down 3? The stretch, right? Because order of operations says do this, then do this. So we're going to stretch it. So I'm going to take these points. Now the origin's not going to move, right? We only stretch compared to the x-axis. So instead of over 1, up 1, it's over 1, up 1, 2, 3, 4, 5, 6, 7, 8. This one's going to be down 8. And then I really can't stretch these points. They'd be, at positive and negative 64. But I can take now this point, and this point, and move them all down 3. So now I'm replacing this point and this point. So my graph is going to look like this, which is very steep. And there's just a teeny tiny little flex point right about there. Okay? So that is g of x. Any ideas for how I could have graphed this to look a little less, like, where I could have maybe seen a little bit more of the behavior of that graph?
Change the scale.
I could have changed the scale, right? Instead of counting by 1s along the y, I could have counted by 2s or 4s or 8s. Absolutely. So if you know you're going to graph a stretch, you can always make it a little easier on yourself by changing the units, the scale first. Okay? Abby, you can push that there.